Okay. Okay. Yes. Hi everyone. Hi. Hi. So last session we started mixture distribution, and we talked about expectation maximization a little bit. But let's start from this start of the slide deck again. Review what we talked about. So we talked about point estimation. And we said, okay, maximum likelihood estimation. So we talked about Bayes rule, which was in equation 1, right? And we said that here, this is the posterior, and we have likelihood times prior over the other prior. And its proof is so simple that when Bayes, for the first time, wrote it, he thought that this formula is ridiculous and didn't even announce it. So it was very simple, but it is very powerful formula. And then we said that if we maximize the likelihood with respect to the parameters, that's called maximum likelihood estimation, right? And then we said, so we assume that they are IID, independent and identically distributed. Then the likelihood will be the multiplication of the all of these likelihoods, and then we said we take the log. We consider the log likelihood usually. Why? For two reasons. First off, the multiplication is a pain in the neck, right? So we want to convert it to summation. Also, we know that we usually work with exponential family of distributions, and they have exponential operator, which is a pain in the neck. In order to cancel it, we need the opposite operator, which is logarithm. So we took a logarithm of likelihood, denoted by a small case of L, and then logarithm of multiplication becomes summation of logarithms, as done in equation 5. Then, rather than maximizing the likelihood, we maximize the log likelihood. Which parameters it gives us? That's the maximum likelihood estimation. We also said that we have maximum a posterior or a posteriori in short math, which maximizes the posterior rather than likelihood. We also said there is, for the Bayes rule, for the posterior likelihood, there is connection between philosophy and mathematics. We also talked about it. And expectation maximization, we said that what if some part of the data are missing or not completely known? Then in this case, we can't use maximum likelihood estimation, because for maximum likelihood estimation, we need to have the likelihood, right? But we don't have the whole thing. Therefore, what should we do? Let's replace the missing parts with the expectation. Then everything will be known, and then we can do maximum likelihood estimation. This procedure is called expectation maximization. And of course, we do it iteratively or alternatively until convergence, right? So this is also related to the alternating optimization. For more information, see my optimization course on YouTube. Okay, so this is expectation maximization. It has, as I said, it has two steps: E step and M step, expectation step and maximization step. In expectation step, we take the expectation of the log likelihood or likelihood with respect to, so it's a conditional expectation, data missing, conditioned on the observed data and the theta. And then equation 9, we maximize. In the maximization step, we maximize the expected likelihood, right? And we do it iteratively until convergence of the parameters. Theta. So now I think here we stop. Am I right? Yes, here. So now this expectation maximization, all of these have a lot of use cases in machine learning. One of them is mixture distribution. For example, have you heard of Gaussian mixture model, GMM? So that's exactly one of them. So mixture distribution, what is that? Let's talk about it. Every random variable can be considered as a sample from a distribution, of course. Whether this distribution can be well known or ugly or complicated, right? So a well-known distribution is Gaussian distribution, but if we have a lot of modes, then the distribution is ugly. It's very complicated, right? Then, by the way, usually in life, distribution is ugly, right? Because it's not, everything is not ideal, so it's ugly. As a result, it's very useful. So the mixture distribution, what is that? Is a weighted summation of k distributions. So consider k nice distributions, we add them up, and then it becomes, the whole thing becomes ugly, right? So G1 to GK, where the weights are W1 to WK, and the weights sum to 1. So basically, of course, the weights must sum to 1 because it's probability, right? And as it is obvious, every distribution is in the mixture has some parameters, so its own parameters. So the parameters of the distributions, of course, are different, because consider two Gaussian distributions, mixture of two Gaussian distributions. They must have different means or covariances. Otherwise, there are two same distributions, then it doesn't make sense. It's equivalent to having one distribution, right? Consider these two Gaussian distributions. For example, the means of them are different. Then the summation becomes something like this with two modes, right? So as a result, this is the mixture distribution. It can be formulated as this: f of x with these parameters theta 1 to theta k, which are the parameters of these distributions, is the summation of the weighted linear combination of these G1 to GK, right? Distributions, subject to this, where these weights are sum to 1. By the way, these weights are also called, mixing probabilities, because it mixes. They mix the distributions. Okay, mixing probabilities. And by the way, who says that the distributions in the mixture should be the same? I mean, the same family distribution. Can one of them be Gaussian, the other one be beta or gamma distribution? It can. But usually, for the sake of simplicity, we assume that they belong to the same family at least. Okay. Okay. EM for mixture distribution. Now let's use expectation maximization for the sake of mixture distribution, right? So we want to fit a mixture of k distributions, G1 to GK, to the data. When I say fit, I mean, okay, this data that we have has some distribution. Let's find its distribution as a linear combination of several distributions. So, sorry. Okay. So, again, in theory, these k distributions are not necessarily from the same distribution, but for more convenience, but by the way, equation 10 for more convenience is repeated here. Okay, I'm repeating that. Now let's take the likelihood and log-likelihood. The likelihood first. The likelihood of this is multiplication of these f's. Okay, for I from 1 to n. Note that this is for one x, right? Now assume I have several x's, x1, x2, x, and they are IID, independent and identically distributed. So as I have said here, x1 to xn. Then as a result, the likelihood becomes multiplication of each of these PDFs, right? Because they are independent. And each of them, according to this, is itself a summation, linear combination of several distributions. So I have multiplication of summation. Agreed? Okay, and where multiplication is over the points and the summation is over the distributions in the mixture. Now I take log likelihood, because this multiplication is a pain in the neck, right? So logarithm of multiplication becomes summation of logarithm, right? As a result, I will have this. So of course, we have two summations. One of the summations here is over the points. The other summation is over the distributions, right? Interrupt me if you need more explanation in any part, okay? So this is what we had. Now, can we optimize this, by the way? Can we optimize this? Can we maximize this likelihood? No, according as I have said here, the summation within the logarithm, this, I have summation within the logarithm, is a pain in the neck, and it's one of the hardest things to handle in mathematics. Logarithm of a times b is easy to handle. Logarithm of a plus b is a pain in the neck, right? So it's hard. Now let's use this trick. This trick, I think the first time was proposed by Hasty and Tipshirani in Elements of Statistical Learning book. Okay, at least I have seen it there. So it's a good trick. Delta ik is defined as this. So if xi belongs to gk, okay, xi belongs to gk, then delta ik becomes 1. Otherwise, it's 0. Okay, understand? So now it's probability. Probability that delta ik is 1 is wk, the weights, right? The weight. Probability that delta ik is 0 is 1 minus wk. Of course, these two should sum to 1 because it's delta ik is either 0 or 1. Now the likelihood. Let's see. The likelihood can be written. The likelihood above can be written in this way. So the summation. This is the summation as before, right? And then this is the logarithm as before, of course. Now this summation, I'm breaking it down into several cases. If delta I1 is 1 and the rest are 0, then I only have the first term in the summation, right? If delta I2 is 1 and the rest are 0, then I have the second term in the summation, etc. until the last one. So far clear? No? Which part is not clear? Delta I. Okay. So did you understand until here? Okay, but why didn't you interrupt me? Stop me and say I didn't understand this part. Okay, don't be shy. So delta, now I want to do MLE, maximum likelihood estimation, right? Right. So I want to maximize L, agree? But I have this sum. Look, do you agree that this is like logarithm of a plus b plus c, what, etc., right? This is hard. How do you handle logarithm of a plus b plus c? It's hard. It's very hard. So in order to kind of handle this hardness in mathematics, let's do a trick. Let's divide the summation inside the logarithm into several cases. Okay. So I define some parameter delta ik. This is definition. I'm defining the delta ik. I is the index for the data point. K is the index for distribution in the mixture, right? Then I said delta ik is 1 or 0. It's binary. If xi belongs to, so I assume this is a mixture, right? For now, assume that belonging is binary. Either it is in this distribution or not, or in the other distribution or not. Okay. If some point belongs to this, to the kth distribution, delta ik is 1. Otherwise, it's 0. So far clear, right? Okay. So, and for probability for this to be 1, delta ik is wk, is exactly the weight in the weight of that this specific distribution in the mixture, right? That's why we call it mixing probabilities, right? And the probability that delta ik is 0 is 1 minus wk, because they need to sum to 1. So far clear. Now, using this trick, I can divide this to these cases. If delta I1 is 1 and the rest are 0, it means that my xi belongs to G1, right? So the summation only take its first term and not the other terms, right? Also, if delta I2 is 1 and the rest are 0, then I will have W2G2, etc. So I broke down the summation, okay? So this is what we had. Now, can I write it using delta? Can I restate the whole thing to this single equation? Yes, why? Because delta ik is kind of indicator function, right? Where whenever it is 0, it's everything multiplied by 0 is 0. It's at infinite, right? So the other terms inside the summation becomes 0. As a result, I can summarize the whole equation in this equation because of this. Okay. Now I have the log likelihood. Can I maximize it? No, there is a problem for maximization. Delta ik is missing data. You remember? You don't know delta ik. It's a chicken and egg problem. It's a chicken and egg problem. What is the goal of finding mixture distribution? You want to know the delta ik's. But for knowing delta ik, you need to know delta ik. For finding delta ik, you need to know delta ik. It's a chicken and egg problem. So it's missing data, right? As a result, we have to do expectation maximization. We can't do maximum likelihood estimation directly, right? So delta ik is the incomplete missing datum because it's 0 or 1 for xi and a specific k, okay? Then, so this is what, so E step, M step. E step in expectation maximization. What is that? So take expectation from this log likelihood. What happens? You tell me. Expectation is a linear operator. It passes through the summations, right? So it comes here, passes through all of these summations. It comes here. Then this part, logarithm of wk gk is what? Is not random. It comes out of the expectation, okay? Note that random variable here is delta ik, right? So I will have expectation of delta ik, but it's a conditional expectation. Do you remember? In expectation maximization, I told you. It's expectation of D missing, conditioned on D observed and theta. As a result, here D observed is the X itself, right? The X1 to Xn, I mean. And theta 1 to theta k also are the parameters. Okay. Now, let's calculate this expectation here. Delta ik is either 0 or 1, right? It's binary. So so the expectation becomes very easy to calculate. According to, do you remember the definition of expected value? Expectation. Summation of x times probability of x, right? So now, how many cases do I have? 2. Delta ik is either 0 or 1. How many values can delta ik take? So 0 times probability of that to be 0 plus 1 times probability that to be 1, right? According to the definition of expected value. Now, this term goes away because of this 0. As you see, whenever, I'm also saying this for your own research, whenever you are working with binary random variables, expectations become very easy to calculate because one of them will vanish because of that 0, okay? Then I will have 1 times it. So as a result, yes. I didn't understand your question. Can you explain more?
And center 1 to center k is equal to probability of delta ik is equal to 1 given x. You only care about data ik is equal to 1, but at the beginning you assume that the delta ik should be 1 or 0.
Yeah, yes, exactly. So delta ik can be 1 or 0, and I have used it here. As you see, this is the first case for 0. This is the second case for 1.
Delta ik is equal to 1.
Yes, it's because its value is 0. So I'm saying that we calculated that, and we saw that the expectation becomes probability that delta ik is 1. When you put it in the formula of expectation, expected value of x is defined as summation of cases of x, probability of x, right? When x is Benjamin, put Benjamin times probability of Benjamin. When x is 0, put x 0, 0 times probability of x is 0, right? But when it is 0, 0 times the probability becomes 0. What do I do? It goes away because x is 0 for them. Understand? I just put that in the formula and it gives me that the expectation is this. We can't complain about mathematics. This is what happens because 0 times that becomes 0. Right? So that's why I'm exactly what I'm saying. When we are binary calculations, usually one of the terms in the expectation goes away. So now, according to the Bayes rule, what happens? So this expectation, which was this, let's calculate it. According to the Bayes rule, probability of delta equals 1 given x and theta becomes the joint probability, right, of x and theta and delta equals 1 over probability of x. Do you agree? Okay. Recall preliminaries. And now I can write it also as a conditional probability of x and theta given delta equals 1 times probability of delta equals 1. In the denominator also I marginalize, right? I marginalize over all of the delta ik. So I condition on delta ik prime, but I'll sum over all of them. I marginalize, right? So I'm repeating it. In summary, we have this. So I'm repeating what we had, these three. Q was this, do you remember? Q was the expected log likelihood, right? And expectation inside the Q was simplified to this probability, and this probability, according to the Bayes rule, became this, right? Now, the marginal probability in the denominator is this. So let's see. Yes. This in the denominator is actually this, right? So far clear? Is this? And what is probability of x? The PDF of x. Do you remember? Where did we start from? Do you agree that this is probability of x? So that's why I can replace it as by summation of delta WG. Agree. So this is what we have. So we can write it as this. By the way, I have used k prime not to confuse it with the k in the numerator. Okay. So now assume that gamma ik prime, I define it to be expectation of delta ik given x and theta. Okay. In other words, this expectation that we had, I'm denoting it by delta ik prime. Sorry, delta ik hat. Why hat? Because we're estimating that. Okay. So as a result, this expectation, according to this, is equal to this, and we denote it by delta ik hat. The denominator we just said that is this denominator, and the numerator is just one of the terms of terms of denominator, right? So delta ik hat is found as in equation 11. Agreed? Now let's plug it back. Plug equation 11 back inside here, inside the expected log likelihood. Then what happens? So rather than this whole thing, I'll have delta ik hat. So this is what we found. Now let's simplify it a bit because it will help later. So I have Q theta 1 to theta k as I have it here. What are we doing here? logarithm of A times B is logarithm of A plus logarithm of B. So logarithm of W times G, I can write it as logarithm of W plus logarithm of G. Right? Okay. Now, the M step in expectation maximization. The E step is over. Okay. Now the second M step in expectation maximization. So by this slide deck, I'm teaching you two things. I'm killing two birds with one stone. I'm teaching you expectation maximization and also mixture distribution. By mixture distribution, I'm giving you an example for expectation maximization. Okay. So now we maximize this Q, where Q is the expected log likelihood, right? Subject to, we had this constraint also, the weights should sum to 1. This function Q is also a function of W's, right? This function Q that we had here. That's why I also have said it's also a function of W1 to WK. And that is why we wrote it in this way. Anyways, doesn't matter. Okay. So I'm repeating it what we had here. Now, this, what is that? Is actually a constraint optimization problem because I'm maximizing this Q with respect to theta and W, theta K and WK, subject to the weights sum to 1. It's a constraint optimization problem. What should we do for constraint optimization problem? What do we always do in this course? No, it's a constraint. It's not unconstrained. When it is constraint, what do we do? Lagrangian, right? Lagrangian relaxes the problem to become kind of unconstrained, right? So recall preliminaries. And I have Lagrangian, but Lagrangian also have some Lagrange multiplier, also called dual variable. Let's denote it by alpha. Okay. So now this is the Q minus alpha times the constraint, because bring 1 to the other side, right? It's the constraint. Agreed? So now I replace Q with what we found in the previous slide. So this is Lagrange. Now that we have Lagrangian, what should we do? We always are doing this in this course. Take derivative. Take derivative, set it to 0 with respect to the optimization variables. So with respect to both primal variables and dual variables, right? So take derivative with respect to theta K. You tell me, let's calculate it. So derivative goes through the summations. And this term, is it dependent on theta K? The first. No, it's constant. So this derivative becomes 0. The second term, yes, it's dependent on theta K. Then we need to do chain rule, right? Chain rule. What is the derivative of logarithm? 1 over G. Yes, exactly. 1 over G, or 1 over the argument. I mean, 1 over the argument. So this is the gamma also. And then derivative of G with respect to theta K. Set it to 0, right? Right? Okay, now derivative. So then the other parameter, optimization variable, WK. Take derivative of Lagrangian with respect to WK. What happens? This has WK, but this one is constant. It goes away, it's derivative, but the first one, it becomes 1 over WK, right? What about this? The last term also is a function of WK. So, and the derivative passes through the summation. So I will have minus alpha, right? Where did the summation go? Can you tell me? Where did this summation go? I don't have it here.
Derivative of W1 with respect to WK, like
yes. So exactly, because when I'm taking derivative with respect to WK, it's for a specific K. For a specific K, as a result, the summation goes away. So let me tell you. So summation of WK is actually W1 plus W2 until plus WK, right? Now assume this K is 2. Derivative of this with respect to W2, only W2. We have W2. The other terms are constant with respect to W2. So that's why the summation goes away. So I have minus alpha, set it to 0. Now rearrange the terms. WK, because WK here can come out of the summation. It's not dependent on I. Rearrange the terms, you will have WK as this. Okay? So far clear? Right. Now take derivative of Lagrangian with respect to the dual variable. What happens? The whole first two terms are constant with respect to alpha. Goes away. And this is linear with respect to alpha. So it becomes this equal to 0. And it gives us back the constraint. Usually when you take derivative of Lagrangian with respect to the dual variables, it gives you back the constraint, usually. Okay. So now, what happens? Plug this inside the constraint. Okay. So I have WK here. Also, I have WK here. So if you do that, you will get this, right? By the way, this means therefore. Okay. We have this. 1 over alpha is not dependent on K, so comes out of the summation. Rearrange the terms. Alpha becomes this. Okay. Now, where were we? Where were we? Okay. Now, interesting. Consider this equation again. We just found alpha here. So replace this alpha here with what we found. You will get this. Right? This formula is one of the most important formulas in mixture distribution. We just proved that, right? Just proved. Why didn't I go further on this? Because it depends on G. Now I'm gonna give you some examples for Gaussian distribution, okay? But for now, I didn't assume what the distribution is. It's general case, okay? So this is what we have in summary. We found WIK hat, which was the expected as far as I remember, that expectation that we had, that expectation term. This is what the derivative of Lagrangian with respect to theta, and we said it depends on G, because here we have the derivative of G, set it to 0. We also have WK hat. And WK hat is a mixing probability, is a weight in the linear combination. Right. Now let's see the algorithm for fitting a mixture distribution. Initialize theta 1 until theta k and W1 until WK. Agree? Then, as I said, expectation maximization is an iterative algorithm. So while not converged, first do E step, then M step, right? In E step, what should we do? We should calculate WIK hat, this one, but WIK hat has both I and K, so it's a nested for loop. For loop over I, the data points, and loop over K, the distributions. So we calculate that. This is E step is over until here. Then we go to M step, maximization step. So theta K hat is found by this equation. WK hat is found by this equation. And as a result, we also should do it for all of the Ks, all of the distributions in the mixture. Then we check convergence. How do we check it? So we had found theta 1 to theta K and W1 to WK, right? Compare them to their previous values, previous values in the previous iteration, I mean. Have they changed a lot or a small change? If the change is too small, it's converged, right? Then if not, do it again. Do it again. E step, M step, E step, M step, E step, M step until you converge, right? Okay. So, and then when you have thetas and W, It's over. Why? Because thetas are the parameters of the distributions. For example, if it is Gaussian, what are the thetas? If it is Gaussian distribution, what are the thetas? What are the parameters? Mean and variance, or in case of multivariate Gaussian, it's mean and covariance, right? What are W1 to Wk? Are the mixing probabilities. So now let's go to a special case, Gaussian mixture model. Okay. So here we consider a mixture of k one-dimensional Gaussian distributions. For now, okay. We can have multi-dimensional Gaussian distributions, but for this, currently we assume one-dimensional Gaussian distribution k, or univariate Gaussian distribution. So this is, as a result, gk becomes this. This is the PDF of the Gaussian distribution, univariate Gaussian distribution. Agree? Do you agree? This is univariate Gaussian distribution. I denote it by phi of k minus mu k, where mu k is a mean, and sigma k is the variance. This is a notation, okay, for all k1 to k. As a result, equation 10, the linear combination of the distributions becomes this, equation 15, right? Then equation 11 also had g in the numerator and denominator. As a result, I replaced their g's with phi's, the PDFs, right? Agree. Now let's see what happens to the q, which was the expected log likelihood. What happens to that? Let's go back to q. I don't memorize formulas. This was q. Do you remember? This was q, right? So I have gamma log of w plus gamma log of g, right? Gamma log of w is the same in all distributions, right? Gamma log of g is now different in GMN. Let's see what happens. So this is gamma log of w as before. Gamma log, this is log of g, and it becomes simple. Why? Because g is a Gaussian distribution. It has exponential operator, and it cancels out by the logarithm, right? So we have this logarithm of this times this. We know that logarithm of multiplication becomes summation of logarithms. So I have this term, and this minus half is because of the square root in the denominator. And also this part because of this, because of this, and also this. That term doesn't have any logarithm because its exponential operator was cancelled with the logarithm, right? So this is what we found. What should we do now? Lagrangian, the Lagrangian. Let's see what happens to the Lagrangian, right? Because we were maximizing this Q, agreed? And it was, do you remember, it was a constraint optimization. So if we write down the Lagrangian that we had in general case in several slides ago, this is the Lagrangian for mixture of Gaussian distributions, right? Again, let's take derivative with respect to the theta, but we have two thetas here, mu and sigma, right? So don't think that we have only one theta per g. We might have several thetas per g. It depends on the distribution. Some distribution might have 3 parameters, right? So here, derivative of Lagrangian with respect to mu, and then with respect to sigma. With respect to mu, what happened? This is constant, 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 this constant. Only this term. Its derivative with respect to mu. Right? It's so obvious, right? So it's a square, it's a quadratic function. So it becomes this. These 2 and 2 cancel each other in the derivative. Also, this minus and this minus cancel each other in the derivative. And also, why do I have this summation remains, but this summation goes away? Can you tell me why?
We're talking more so specific case.
Exactly, because derivative with respect to mu k for a specific k. For a specific. Set it to 0. Rearrange the terms, so mu k, bring it out, etc. Because mu k can come out of the summation, because summation is over I. Then you will get this. This is an important formula in GMM. Okay. This. Then also take derivative with respect to sigma k, constant, constant, not constant, not constant, constant. So only these two terms. Take derivative of logarithm, etc. It's so obvious what you should do. Also, you have quadratic sigma in the denominator, so it becomes cubed sigma in the denominator, right? Agreed? 1 over x squared becomes x to the power of -2, for example. Then becomes -2x to the power of -3, something like that, right? So this, and set it to 0. Sigma k can come out of the summation because summation is over I, and again, the summation over k went off because it's derivative with respect to a specific k. Then set it to 0 and you will get this. Rearrange the terms, you will get this. Okay? WK hat is the same as before. So this is what we had. As you see, these two are usually the formulas remain the same for different distributions. Only this part is different. G, what PDF we use in the gamma, right? But these are new. These are the results of derivative of Lagrangian with respect to theta, set it to 0. Okay. Again, you use the same algorithm, but with these things. So here, this part line breaks down into two lines. Theta k breaks down to the mu k and sigma k, right? And here, compare theta 1 to theta k to previous values. I mean, compare mu 1 to mu k with previous ones. Also compare sigma 1 to sigma k with the previous iteration. Now, a simulation. This is my own simulation because I have written a tutorial paper for that. You can see, I will introduce it in a few minutes. My own sim. Me? Tutorial papers are for teaching, explanation. So this is usually my tutorial papers are also survey papers. Many of them, because I disagree with the way that people write survey papers in the literature. That's just for the sake of publication and getting citations. Survey paper should be tutorial paper at the same time. Because, for example, they say, this paper has done this paper has done that, this paper has done this. This is crap. Why? How is it useful? You should say this paper has done this, and this is how it is done, right? This paper has done it, and this is how it is done. You should write the formula. You should explain the mathematics. Use what if you write only one sentence that this paper has done this, useless in my mind. So that's why many of my tutorials has in the title tutorial and survey. So, and many of my tutorial papers became a book. Elements of dimensionality reduction and manifold learning. I will write a few more tutorial papers in the near future, hopefully. Maybe, I think, concentrated on deep learning. And yes, hopefully if I can. Such as new emerging things, if I can do, such as diffusion models and graph neural networks and these things. So be tuned. They will come in archive later. I don't know when, but I will write tutorial papers. So where were we? What were we saying? Okay.
This form.
Yeah. So this this is, as I said, I have a tutorial paper named Fitting a Mixture Distribution to Data tutorial. And I don't know if you can, it's good time because I remember that was my first tutorial paper. First ever tutorial paper was this, Fitting a Mixture Distribution to Data. And let me tell you some history, my memories. Good times. This was assignment of one of the courses that I passed. The professor gave us a question, no solution. I tried a lot. I looked at elements of a statistical learning book. I looked online. I talked to professor. Professor helped me a lot. His name was Mu Zhu. He was very good in University of Waterloo and in the Department of Statistics. All of these things, after the semester, I wrote it as a tutorial paper. And that was my motivation to write further tutorial papers. And then let me tell you funny things. Then Archive blocked me. Said that, can you believe? Because Archive usually doesn't block, doesn't reject. Archive is preprint. Everyone can submit. I'm one of the people who where Archive rejected me several times. I think I have been rejected maybe for 5 or 6 times. And Archive is sensitive for a rejected paper. If it rejects a specific paper of yours, you shouldn't resubmit it. Otherwise, you will be blacklisted. Okay. Anyways, I didn't resubmit my rejected papers, but if you see, some of my tutorial papers are not in Archive because they have been written. For example, I have written a tutorial paper which was very good paper. I don't know why they rejected it. On hidden Markov model, they rejected it. I had to put it on some other preprint server. Anyways, but we put papers in Archive, tutorial papers, but after a while, Archive said, we don't accept tutorial papers. They sent an email to my supervisor, said that, why is he submitting tutorial papers? This is preprint. This should be for pre-publication. Then we said, okay, you want that? Okay, we will publish it as a book. And that motivated us to write the book Elements of Dimensionality Reduction and Manifold. Okay. Anyways, that was a funny thing, that how we wrote the book. So a sample with size n equals, by the way, I wrote this simulation in R because that course was in Department of Statistics and the statisticians love R. They don't like Python. Okay. And if you go to my GitHub, the code of this paper is in R. So a sample with size n equals to 2,200 from 3 distributions, 3 univariate Gaussian distributions are generated like this. So what do I mean by this? The mean is -10. The standard deviation is 1.2 from that. I have 3 distributions. Then for having generality, the size of the subset of sample generated from the 3 densities are different. So what do I mean? What am I doing? I'm having 3 PDFs. I'm generating some data points, and then I'm gonna fit a mixture of Gaussians to them again. Hopefully, the fitted mixture becomes very similar to the actual 3, the combination of these 3 distributions which I generated the samples from. Right? Did you get it? So applying the expectation maximization algorithm and using equations 16, 17, 18, and 14 that we had for mixture of 3 Gaussians, it gives us these. These are the converged values, mu, sigma, and the mixing probabilities. Okay? Okay. Now compare these with the actual means and variance. So the converged one is -9.99. The actual mean was -10. Right? The standard deviation is 1.17. It was actually 1.2. Agree? So it's correct. Also, I have shown my convergences as a plot. Consider these. So these are the 3 Gaussian distributions that I sampled from to generate my data. And then what is this one? This is for sigma 1. convergence of sigma 1. So sigma 1, sigma 2, sigma 3, I mean. So one of them is sigma 1, one of them is sigma 2, sigma 3, doesn't matter, okay? And as you see, they have converged to their values. They don't change after convergence, do you see? Also, this is for mu1, mu2, mu3, the means, right? They converge. Also, this is for mixing probabilities, W1, W2, W3. Did you understand? And what happens then? Let me remember. So the dashed purple density, I mean this one. Do you see that? This one is the mixture distribution. Can you tell me why is it lower than the actual Gaussian here? The modes match, as you see, almost, but it's lower. It must be, because when I was sampling from this, it was one single PDF whose integral should be 1. But now in the linear combination, the whole thing should integrate to 1. Right? It's a linear combination. Yes, okay. So, and the GitHub page, you can go and see my code in our language for that. So some slides are based on our tutorial paper, fitting a mixture distribution to data tutorial. I think, yeah, as far as I remember, I wrote it in my second year of PhD. Yes. See our tutorial of, for mixture of, oh yeah, this tutorial paper has additional things. So it's not just this, it has mixture of GMM, Gaussian mixture model, for multivariate Gaussians also. Also, I have explained a mixture of Poissons. You know Poisson is a discrete distribution. So who says that mixture distribution should be continuous? It can be mixture of discrete distributions. If your data is discrete, if your random variable is discrete, one of the distributions for discrete, which is the most famous, I can say, is Poisson distribution. It's written as this, I think. Poisson distribution. And I have explained how to derive the formulas, prove them for Poisson distribution. Mixture of these discrete distributions and for Poisson. Yes. Some slides are inspired by teachings of Professor Mu Zhu at the University of Waterloo Department of Statistics. For more information on mixture distributions in machine learning, you can see the book of Hasty and Tibshirani, Elements of Statistical Learning. The code of fitting mixture distribution is this in GitHub. Also, scikit-learn has GMM, Gaussian mixture model. So you don't need to implement it. You can use it by a library. It's a library, scikit-learn, or a scalar, whatever we call it. And these are the references. Any question? No? Let's go to the next topic. The next topic is PCA, which is very cool. So far, we talked about preliminaries, overfitting, regularization. Then we talked about regression, basic regression, linear regression, ridge regression, lasso regression. Then we moved to classical classification algorithms. Afterwards, we talked about point estimation. Then we talked about Gaussian mixture model and mixture distributions. Now we enter dimensionality reduction, which a part of my thesis was on that. Also, my book is on that, my existing book. Elements of dimensionality reduction and manifold learning. Of course, we can't cover the whole dimensionality reduction. We cover important ones. So you see the techniques, what they are doing. And I use this as an excuse to teach you techniques. For example, technique of kernelization. So when I'm teaching you not only do I teach PCA, but also I teach you how to kernelize, or also FDA, how to kernelize using representation theory. Why am I teaching this? in your own theory, in your own research, assume you propose an algorithm. Using these techniques, you can also propose the kernel version of your algorithm. Okay. So have a broader insight to these lectures. It's not just one algorithm. PCA. First, let's talk about projection and reconstruction in PCA. If there exists n training data points, x1 to xn, then projection of a training data point is this. So for linear projection, recall preliminaries, right? X tilde is U transpose X. I don't know what I call it. Let's call it breve. Why? Because its LaTeX is breve, /breve, breve. I don't know how to pronounce it, but it doesn't matter. What do I mean by X breve? I mean its mean is 0. I have removed its mean, the mean of the data. Okay, we have to remove the mean, as I said here. This is the mean of training data set. So I subtract the mean of data set from all of the data points. X breve. It's a d-dimensional. After projection, it becomes p-dimensional, where u is d by p. So as this, according to the preliminaries that we had, projects X breve onto the column space of U. And when we have, if U is truncated, meaning that it has P columns rather than D, then we are projecting onto a subspace, a P-dimensional subspace. And the mean, mu X is the mean of training data points. N is the number of training data points. Reconstruction is what? Recall preliminaries. It was U transpose X breve, but there is a but. We have to add back the mean, right? Of course, we need to add back the mean because the mean was removed already before projection. If you forget to add back the mean, assume you do it on facial images. Okay, you reconstruct them back. You don't add back the mean of the faces. It becomes such as X-ray faces. You have removed the means of the pixels. You can't see the actual intensities. Okay. So in PCA, why should we remove the mean? Because of this simple example. Figure A, I haven't removed the mean. If you apply PCA, it gives you crap. But if you center it, it gives you the directions of variance. Why this happens? Why figure A happens? First off, in a vector space, a vector space must have origin. Why? When I mean say origin, I mean 0, 0, 0, 0, right? Every vector space must have origin. Can you tell me why?
Because direction is subjective.
Direction is, can you explain a bit more?
Vector is a scalar with a specific direction, right?
Okay.
So if there is no mean, then mean is the starting point in a distribution.
No, it's not distribute. It's not. I'm not talking about distribution. I'm talking about the space. Assume I have a space like here, 3D, whatever, and in this space has vector. So every point can be represented as a vector. It must have origin. Let me explain.
Because to get a projection of that vector onto a plane, you have to have origin, right?
Yeah, but for example, we assume this is a vector, this is a vector, this is a vector. You can still project it onto this without origin. The starting point, but let me explain it in a more mathematical way. A vector space, in a vector space, the linear combination of all of vectors must lie in the space, in the same space. Okay, the linear combination. So A x1 plus B x2, etc. They should be in the same space. A simple example is x minus x. X minus x also must be in this space. So every vector minus itself must be in this space, which is origin. This simple explanation says that every vector space must have origin, right? That's one thing. And when we project onto the PCA subspace, when we say subspace, its name says it's a space, right? So the space must have an origin. So PCA subspace has an origin. As a result, the principal directions must pass through the origin. Okay. And that's the reason that it becomes crap when you don't center data. Okay. By the way, let me tell you, I have said it here. Sometimes it doesn't make sense to center data. In ancient natural language processing, not nowadays, in ancient natural language processing, people used PCA, okay? At that time, they said that how does it make sense to remove the mean of a word? We don't have negative word, something like that. Therefore, for those specific cases, they didn't subtract the mean, and they called that algorithm latent semantic analysis, also called latent semantic indexing, right? LSA or LSI, okay? So PCA without removing the mean, useful for natural language processing, is called latent semantic analysis. Okay. Did I talk about centering matrix in the preliminaries? I think I talked about it. You remember? I talked about it. So we can use centering matrix H, which is defined as this. Recall preliminaries. Identity minus 1 over n, 1 transpose. This is the matrix of whole ones, but this is the matrix where diagonal is 1 only, and the rest is 0. So XH, what does it do? We talked about it in the preliminaries. It removes the mean of columns. HX removes the mean of rows. HXH removes the mean of rows, the mean of columns, adds back the total mean. That was called double centering, right? Okay, this is, so we have X as, so rather than removing the mean of the data points 1 by 1 in a for loop, we can do it using matrix calculations. We don't need to have a for loop, because matrix multiplication does the implicit for loop for us, right? As a result, I can say XH, or which is equivalent to X minus mu X, and I denote it by X breve. It is still D by N, and because X or X breve have the data points stacked column-wise, right? And every data point is D-dimensional. So X breve is the centered data set. Now, the previous slide was projection of a single point to the PCA subspace. Now I want to project the whole data. So U transpose X breve matrix becomes X tilde matrix, P by N this time, because now I'm assuming I have P columns in U. U is truncated from D columns to P columns. For understanding what I'm saying, it's better to watch preliminaries, see preliminaries, recall preliminaries first. Okay, and then X hat is U transpose X breve, or in other words, U X tilde, but plus mu X, we add back the mu X, right? Right, and X tilde are the projected data, and X hat are the reconstructed data. Now, what if we have a new test data point, which is not used in the training phase, right? This test data point is also called out of sample data in machine learning. Out of sample data means test, not used in the training. So I denote it by xt. Now I calculate xt breve. What is xt breve? This one. I have removed the mean, right? But what do I mean that I have removed the mean? xt minus what? Mean of what? Mean of what? That's important. Mean of training data. Right? Assume I have a test data set, a bunch of test data points. Should I use the mean of these test data set? No. Because I found u using training data. Okay. So x brevet t means that xt minus the mean of training data. Okay. And so u transpose x t brevet, it gives us the projection. We can also reconstruct it and add back the mean of training. Right? We can also write it in matrix form as before. Okay. As I said here, I have removed the mean of training from the test data. Now PCA using eigen decomposition. So we can have PCA, we can formulate PCA in several ways. These several ways will end up with the same solution. Okay, all of them will end up with PCA subspace. Let's find one. Let's work on each of them. One way to calculate PCA subspace is eigenvalue decomposition. Another one is singular value decomposition. We'll talk about them. So eigenvalue decomposition. For now, for simplicity, assume my PCA subspace dimensionality is 1. Okay, is 1. So I have only P is 1, then I have U, matrix U becomes a vector U. So, right? So it has only one column. Agreed? Column. So what is my X hat? Is U transpose X brevet, right? By the way, for now, ignore adding back the mean. Okay, for now. I mean, it's a construction, right? For now, for this analysis, ignore the adding back. Assume that the data was originally centered, even in the first place, okay? It didn't have any mean. Now let's calculate the squared length or squared L2 norm of this reconstructed vector. What happens? Squared L2 norm of X hat is a squared L2 norm of U transpose X brevet, right? We know that whatever, a squared L2 norm of whatever is whatever transpose whatever. Recall preliminaries. So I have this transpose this. Transpose reverses the order of matrix multiplication. So I'll have these. So it becomes X brevet transpose. U transpose becomes U transpose. Interestingly, I have U transpose U, but it is 1 because U is a unit vector. We will see at the end why this happens. U in the every projection direction, every column of the matrix U is an orthonormal vector. We'll see that. Okay. So U transpose U is 1. Then I will have X brevet transpose U transpose X brevet because this became 1, right? Can I write? So this is the inner product. In inner product, I can change the order, right? Because it's a scalar. Because X brevet transpose U is a scalar. U transpose X brevet is also a scalar. Right? So I write it. Also, I change the order of these two. Agreed? Right? Now, let's consider, assume now I have n points rather than 1 point. So I have summation of a squared L2 norm of xi hat. Okay, I goes from 1 to n. Then I replace this with equation 15 that I found. Agreed? Agreed. Then can I so I bring U and U transpose out of the summation because they don't depend on I, and I left factor out U transpose and right factor out U. So I'll have this. Okay. Now, yes. Now consider the matrix of data centered. X matrix X brevet, which is D by N. Agreed? Agree? So can you tell me that, do you agree that this is the covariance matrix? Forget this for now. You tell me, what is the formula for covariance matrix in the scalar, in the matrix form? I have a bunch of data points, vectors. How do I calculate the covariance matrix? Okay, 1 over n, summation, you tell me. I from 1 to n. Okay, xi minus. Yes. Correct. Thank you. Right? And if it is n, it's biased estimation of covariance. If it is n minus 1 in the denominator, it's an unbiased estimation of covariance, right? Now you tell me. Assume, so xi minus mu, I write it as x breve, right? Do you remember? I said x breve, in x breve, we have removed the mean. In other words, it's summation of x breve transpose. For now, ignore the scale, 1 over n. It's a scale, right? So this is this exactly. So it's covariance matrix. In other words, let me tell you in this way. If before calculation of covariance matrix, if you remove the mean, covariance matrix formula becomes very simple. It becomes 1 over n summation of xi transpose. If you already remove the mean beforehand, right? Because the mean minus mu goes away, it will be 0. Interesting, right? Anyways, so I have this. Now what happens? So this can be written in matrix form. As x matrix x breve transpose, right? What was x breve? It was xh. So xh transpose, but transpose reverses the order of matrix multiplication. It becomes h transpose x transpose. But recall preliminaries that h centering matrix was symmetric. We proved that in the preliminaries. So h transpose is h. Again, recall preliminaries that matrix H, centering matrix, is idempotent. We proved that. So H times whatever, how many times you multiply H to itself, it becomes H again. It's idempotent, okay? So H becomes H. We proved that in the preliminaries, right? So this is covariance matrix before projection. Covariance matrix of data. Now compare this with what we have in equation 16. We just talked about it. This is S. Projection matrix before projection. Covariance matrix before projection. Right? Covariance matrix of data. So basically, this, which we started from, is U transpose SU. So summation of a squared L2 norms of the reconstructed data is U transpose SU. Okay. We can interpret it in another way too. We can interpret U transpose SU in another way. Assume I have data X. I project it by U transpose X, right? It's linear projection. What happens to S after projection? When you project X by U transpose X, what happens to S? X, so linear projection is linear, right? That's why I have U transpose X. Covariance or variance is quadratic. Do you agree? Has squared or something transpose, right? So as a result, this, whatever I write it here, it should be quadratic. So rather than U transpose S, it will not be U transpose S, because U transpose S is linear. It's not quadratic. It will be U transpose SU. So you can interpret this as covariance matrix after projection. So covariance matrix before projection is S. Covariance matrix after projection is U transpose SU. If your projection matrix is U, or projection direction is small u, doesn't matter. Did you understand? Okay. Now, I want to, so by the way, we can have several various optimization problems for PCA. We go over them one by one. One of them is this. I want to maximize, I want to find my projection matrix in a way that it maximizes the variance of data after projection. Did you get it? What was covariance or variance after projection? It was U transpose SU, right? So let's maximize it with respect to U. Agreed? Now you tell me, if I only say maximize U transpose SU, what will be the solution? Maximize U transpose SU with respect to U. What is the solution of what U? What? U? No, I'm saying that which U maximizes U transpose SU? What? You tell me what? So a matrix of all elements 10, assume, becomes big. What about a matrix of all elements 100? Becomes bigger. What about a matrix of all elements 1000? Becomes bigger. So the solution is the matrix of infinity. All elements. So U becomes infinite. So it's an ill-posed optimization problem. For this to be well-posed or well-defined, whatever we call it, we need to add some constraints. Right? So let's add the constraint. I assume that my U, vector U, has length 1. Its L2 norm is 1. So I know L2 norm of U, the squared L2 norm of U is U transpose U. Let it be 1. So far clear? Now it's well defined. I have, this is a constraint optimization problem. What should I do? What? Lagrangian. We see it a lot. In dimensionality reduction, you see it too many times. Okay, so Lagrangian U transpose SU minus lambda U transpose U minus 1. Lambda is a dual variable, a Lagrange multiplier. What should we do? Take derivative with respect to the optimization variable, U. We know that U here is a p-dimensional vector. Derivative of a scalar with respect to a p-dimensional vector is a p-dimensional vector. So this is quadratic with respect to U, it becomes 2SU. This is also quadratic with respect to U, it becomes minus 2 lambda U. Set it to 0, it becomes SU equals lambda U. Right? What is this? Recall preliminaries. As you see, preliminaries are very important in my courses. So SU equals lambda U. What is that? That is eigenvalue decompose, eigenvalue problem. Eigenvalue problem for matrix S. Did you read, study the preliminaries? Do you remember we had it? We had this format. So this was the eigenvalue problem for matrix S, where U is eigenvector and lambda is eigenvalue. Right? So what did we want to find? U, right? The optimization variable was U. We just solved it and saw that the solution to the optimization problem, U, is the eigenvector of matrix S. And what was S? The covariance matrix before projection, the covariance matrix of data. Right? Done. PCA over for now. PCA solution is the eigenvector of covariance matrix. Okay, we just proved that. Okay. And this is also called PCA direction, or principal direction, or principal axis in the literature. People call it different names, doesn't matter. The mathematics is important. Okay. The projected data also, sometimes they call it principal components, hence the name principal component analysis. Right. So now assume I have multiple directions. So my PCA subspace is multidimensional, p-dimensional. P is not one necessarily. Then it becomes U transpose X breve again. Do you remember we had a squared L2 norm of X hat? Here we will have a squared Frobenius norm of X hat. Recall preliminaries for Frobenius norm, right? Then again, it becomes this. Again, we'll have trace. If we calculate, simplify, we know that U transpose U is I because we are going to use the constraint U transpose U equals I, which means U is an orthogonal matrix. Its columns are orthonormal. Recall preliminaries. Okay, so we calculate that. Then it's this. So we can interpret it in, again, two ways. Either it's squared Frobenius norm of X hat, this trace of U transpose SU, or it's, you tell me, or it is covariance matrix after projection, right? So S is covariance matrix before projection, U transpose SU is covariance matrix after projection. I want to maximize this covariance matrix after projection. Also, I want this to be a scalar. So that's why I have trace here, right? Otherwise, U transpose SU is a matrix. And I want the matrix U to be orthogonal. Its columns to be orthonormal. So the projection directions will be perpendicular to each other, and each will have length 1. Right? Form the Lagrangian, because this is, by the way, optimization variable now is a matrix rather than a scalar, rather than a vector, right? Whose columns are the projection directions. Now, we know that what is the Lagrangian? This, what we have, this is a constraint. Now my dual variable becomes a matrix. My Lagrange multipliers becomes a matrix, lambda transpose, and I have trace also, because do you remember? Inner product for matrices has trace. This is inner product between lambda and the constraint, right? So I must have trace. Take derivative with respect to U. U is d by p. Derivative of a scalar with respect to a matrix is a matrix again, right? So when this is quadratic with respect to U, it becomes 2SU. This is quadratic with respect to U, also it becomes minus 2U lambda. Set it to 0, rearrange it, will give you this. U becomes it. This is an eigenvalue problem for S, but now U is a matrix of eigenvectors. Now I have several eigenvectors, P eigenvectors in other words. And lambda is a matrix of eigenvalues whose diagonal elements are the eigenvalues. It's a diagonal matrix. For proof of why lambda is a diagonal, either look at my tutorial paper for eigenvalue and generalized eigenvalue problems, or the chapter background on linear algebra in my book, Elements of Dimensionality Reduction, or you can say it must be diagonal because it's an eigenvalue problem. Okay, that's so far clear? Because in eigenvalue problem, you know that this is a diagonal matrix, eigenvalues. Okay. Yes, I think I said it. Okay, and now, by the way, when you solve this, S is d by d, right? As a result, U will be d by d, not d by p. But if you truncate it, it becomes d by p. So far clear? So S is d by d, U will be d by, we will have d eigenvectors. Lambda will also be d by d. I will have d eigenvalues, but I can truncate it. By the way, we have to sort them. We have to sort these eigenvectors and eigenvalues. How do we sort them? As it is maximization problem, we need to sort the eigenvectors where the eigenvalues are decreasing. So the largest eigenvalue, then the next largest. So in descending order, the eigenvalues should be sorted because of maximization. If it was minimization, the sort must be ascending. But this is maximization. The sort is descending. And we sort the eigenvectors corresponding to eigenvalues, right? Sorted eigenvalues. And then we can truncate. So you need to sort first and then truncate. Then what do I mean by truncation? Remove the least important eigenvectors with the smallest eigenvalues, right? So you will have only p eigenvectors. Now assume I have p eigenvectors. What is the PCA subspace? Is a subspace whose basis vectors are these p u1 to up. In other words, it's a span of u1 to up. Do you remember a span? We talked about it in preliminaries. The space spanned by u1 to up, the columns of truncated u. It's the PCA subspace. Okay, as you see, it's why do we call it subspace? Because p is less than d. Truncated that subspace. It has lower dimensionality, sub, right? As I said, we can truncate u. I think I already talked about it. We can truncate u. We can also talk about the rank. So assume u is d by d. By the way, if we don't truncate it, assume u is d by d. What happens? PCA is not subspace anymore. But there is a but. It does something for us. Consider this example. This is 2D, two-dimensional. These are the points, okay? I have the principal directions, okay? As you see, PCA rotates data. So linear projection without truncation is equivalent to rotation in the same space, right? It's very important and useful in industry too. I have used it at least in 2 of my papers. You can use PCA for rotation. For example, you have a cloud of points, but these cloud of points which are coming in your research paper or in industry you see it a lot. These are like these, sometimes it's like this, sometimes it's like this, but you want to compare them. You can't. Sometimes it's aligned in this way, sometimes aligned in this way, sometimes aligned in this way. First, you need to align them, all of them. In other words, you want to cancel their rotations. How do you do that? You apply a PCA, then you know the degree, the angle, because you can calculate the angle of your principal direction, right? Of course, you will consider the most important principal direction here, at least in this case, because the most important will be this, right? Then you calculate the angle of this most principal direction, then you cancel it. You know how to rotate data, right? Sine, cosine, minus cosine. I forgot the formula, sine, cosine, right? So you can do that. So PCA is a very good technique to remove the rotation. There is a paper in face recognition where they have removed the pose of face by PCA. It's very interesting, right? So you can do it. But yes, if you truncate, then the rank of UU transpose becomes P, which is less than D. Okay. By the way, I also have said that what if your data is kind of spherical, like this? So it doesn't have a specific direction of variance, right? In this case, all of your eigenvalues will be large. Then in this case, it means that you shouldn't truncate, at least. Or if you truncate only one of them. So in other words, it's not worthy for dimensionality reduction. All dimensions are important. Okay. Yes, I think I already have said many things. And yeah, I think I said the important things. If here I have said, if one of the eigenvalues is small, you can ignore that. And so, for example, what happens to this if I ignore P2, I truncate it to only be P1, then the points will be projected here after projection, right? So far clear? Then I can forget these axes. Then what do? Look at my face. So I'm looking at this figure exactly, looking at this. Hopefully, so looking at this, right? Rather than looking at this, I rotate my head like this. Okay, I look at it like this. Then it means that it becomes this. Of course, it has origin. So maybe origin is here, right? So the points became one-dimensional. You understand? Okay. Reconstruction error in PCA. So as I said, do you remember recall preliminaries, linear projection? We talked about it. We always have reconstruction error. When you project onto subspace and project it back, you might not necessarily be at the same point. You have some reconstruction error. We talked about it in the preliminaries, right? So R is x minus x hat, which is x plus, at least in PCA, x. Yes, what is x? You can write it as x breve plus mu, right? X breve is without mean. And x hat is UU transpose x breve plus mu. X. But I have minus here, minus, right? So these two cancel each other. As a result, the residual reconstruction error or residue can be seen as x breve minus UU transpose x breve. Okay? So if I don't truncate my U, the reconstruction error will be 0, of course, because it's like rotating and rotating back in the same space. Okay. So consider this principal direction. As I said, this, by the way, this reconstruction error is different from the error in linear regression, the mean squared error. So this is principal direction. These are the reconstruction errors. Do you agree? But now assume I want to fit a line like in linear regression to these points. Then what were the mean squared errors in linear regression? It's like this. Do you see the difference? The reconstruction error is perpendicular. But the mean squared errors in the linear regression are not perpendicular necessarily, right? That's another thing. Now, as I said, we can have various optimization problems for PCA, for forming PCA. The other one is this. So one of them that we previously talked about it was maximization of covariance after projection, right? Now this time we say we can also see PCA in another way. We can minimize the reconstruction error. Okay, so let's minimize this. What is this? X breve minus UU transpose X breve is the reconstruction error. We talked about it, right? But a squared Frobenius term, because I want it to be scalar, right? The error. And again, for this to be well defined, I add the constraint UU transpose should be I. The matrix U should be orthogonal matrix. Then what happens? Let's simplify it. Let's see what happens. Consider the objective function, the squared Frobenius norm of X breve minus UU transpose X breve. What happens? So squared Frobenius norm of Benjamin is Benjamin transpose Benjamin, but it has trace because it's matrix. So trace of this transpose this. Again, I apply trace in the parentheses. I know that transpose. I apply transpose on the parentheses. I know that transpose reverses the order of matrix multiplication. So I will have this. So it becomes X breve transpose. U transpose becomes U and U transpose. Okay. Now I multiply the elements to each other. So I'll have 4 elements, right? Interestingly, I have U transpose U in the middle, which was the constraint. According to the constraint, it's I identity. So it simplifies. Again, interestingly, here I have minus 2 X breve transpose UU transpose X breve. Here I have 1 X breve transpose UU transpose X breve. So they simplify to only minus, right? Minus 2 plus 1 becomes minus 1, right? Trace is a linear operator, so it can be applied on this, sorry. It can be applied on this and this separately. Now I can use also the cyclic property of trace. So I bring it here, then, yeah, I brought it here, as you see. Now, consider this optimization problem. It's a constraint optimization problem. So let's form the Lagrangian. Lagrangian is, this is the cost plus trace of lambda transpose the constraint. And what is lambda here? Again, Lagrange multipliers, dual variables, right? So this is what, now what should we do? We have the Lagrangian. What should we do? Take derivative of Lagrangian with respect to optimization variable, set it to 0. I think now you have memorized this sentence. I have said it so many times, right? So take derivative with respect to u, it gives you this. By the way, if you can use my technique for taking derivative, right? To check in the dimensionality, fake dimensionality, to see how to take derivative in matrix. You don't need to go to the matrix cookbooks for that. Set it to 0. By the way, this must be a 0 matrix, sorry, d by p. So it gives you this. What was X breve transpose? It was S, covariance matrix. So it gives us this. What is this? Eigenvalue problem for S. A nice thing is that we started with this optimization problem. We ended up with the eigenvalue problem for S. We started with the other optimization problem. We also ended up with the same solution. 2 different optimization problems ended up with the same solution. As a result, we can have 2 different optimization problems for PCA. So you can interpret PCA in 2 ways. Either PCA maximizes the covariance after projection or minimizes the linear projection, the reconstruction error of linear projection. Did you get it? I mean, after truncation. Of course, if you don't have any truncation in U, any matrix U will have 0 reconstruction error because it's just rotation back. I mean, what U will have the least amount of reconstruction error even if you truncate it. That's the PCA solution. Did you get it? Okay. As a result, you tell me. Assume I have an autoencoder. Neural network autoencoder. So I have encoder. I have decoder. I have X, I have X hat. Okay. I train it by backpropagation. Assume I don't put, I forget to put activation function in the middle. One layer, here, let it be U. Let it be U transpose, right? So the one layer only, and I forget to put nonlinear activation function. I train it by backpropagation after several iterations. Interestingly, what backpropagation learns will be the PCA directions. Because we just proved that for minimization of X minus X hat, if it is linear projection, it must give you the PCA solution. So basically what backpropagation will learn will be the eigenvectors of the covariance matrix, right? But if I put a nonlinear activation function here, such as ReLU or other, forgot the names, or sigmoid or these things, or hyperbolic tangent, etc., then what happens? Then it will not have, because it will not be linear projection anymore, right? Agree? Now assume I have multiple layers, not just one layer. So multiple layers. encoder, multiple layers decoder. Again, I forget to put activation functions in the middle. The solution still will be PCA. Why? Because you can see this as U1, U2, U3, etc. The whole thing you can see it as one U. There is no non-linearity between them. You can see the whole thing also as U transpose. That's why it's important not to forget activation functions in neural network. Otherwise, it's nothing different than PC, for at least for autoencoder, right? For us. And it's important that PCA has the least squared error in reconstruction. It's very important, very important. Okay. Already said it. I already said it here. What I said about the autoencoder is here. So PCA is equivalent to an undercomplete. And by the way, this is undercomplete autoencoder. I will tell you what it means. With one hidden layer without activation function. So this is undercomplete autoencoder. This is overcomplete autoencoder. Encoder, decoder. Encoder, decoder. Undercomplete autoencoder is for compression, right? For dimensionality reduction. Oh, how is overcomplete autoencoder useful? Can you tell me? How is overcomplete autoencoder useful? Can you give me some? Okay. Okay. I put X here. I put X hat. Assume I'll train the autoencoder by backpropagation. What will happen? Can you guess? Put yourself in the shoes of neural network. Now you are neural network. You want to train, you want to reconstruct X here at the end, and you have the control of your weights. You are backpropagation algorithm. What do you do? As it is overcomplete, you have more neurons than here, than X, so you can simply copy. You can simply copy. So if you train it by backpropagation, many of the weights will be 0, and some of the weights will be only 1. You're just copying, right? But so you might think, you might say that overcomplete autoencoder is useless. No. What if I add some noise here? X plus some noise as input, but I want to reconstruct X hat. So I want to get X, not X plus epsilon. In this case, it will not be able to copy, right? As a result, overcomplete autoencoder is good for denoising, because X hat will be X, reconstruction of X, not X plus epsilon. So you remove epsilon, you remove the noise. Okay, so it's good for denoise. Also explain this. If you have multiple layers, you can, without any nonlinearity between them, you can see it as one U. Right? So here, if we have X, here we have U transpose X, here we have U transpose X. Agree? Let's have a break and come back at 9. Okay. Thank you. Okay. So, shall we start, guys?
This guy is here, but
Oh, where is he?
I think just call him.
Okay, thank you. I appreciate you. Okay. What should I do? Should I explain or?
Please.
Shall I start?
I think
Yeah. Okay. So we can have PCA using singular value decomposition, SVD, rather than EVD, eigenvalue decomposition. So what do I mean? Consider X breve, okay, which was the centered data, right? Consider the singular value decomposition on the X breve itself, not the covariance matrix, X breve itself, the centered data. Centered data is D by N. Right. So here I are saying that consider SVD on the data, centered data, X breve, rather than covariance matrix. Okay, not the covariance matrix. Singular value decomposition on the data itself. You will have U sigma V transpose, where U has the left singular vectors D by D, singular vectors of X breve. V are the right singular vectors, and sigma are the singular values. Okay. Do you remember in the preliminaries we proved that with a relation of SVD and singular value decomposition and eigenvalue decomposition? Do you remember? So we said that the left singular vectors, which are U for X breve, are equivalent to eigenvectors of X breve transpose. And V are equivalent to the eigenvectors of X breve transpose X breve. For proof, see preliminaries lecture, right? Now, you tell me, what was the solution of PCA? Eigenvectors of covariance matrix before projection, right? What was covariance matrix before projection? It was X breve transpose. Do you remember? So this is covariance matrix before projection. And we know the solutions of PCA were eigenvectors of X breve transpose, the covariance matrix. As a result, the solution of PCA can be seen as the left singular vectors of X breve. Right? So rather than eigenvalue decomposition of covariance matrix, I can apply singular value decomposition on the data, centered data itself, and take the left singular vectors as the PCA directions. Okay, understood? Interestingly, if you do that, you don't need to sort anymore. The eigenvectors or singular vectors will be sorted anyways, automatically. SVD sorts eigenvectors. Okay, did you understand? So the left singular vectors will be already sorted. And yeah, I already explained this. So we talked about PCA using eigenvalue decomposition, also PCA using singular value decomposition. Now determining the number of principal directions. So in PCA, the components with the smallest eigenvalues can be cut off, right? The truncation. Do you remember? So we have several ways to do that. How do we find the P? How many PCA directions do we keep and remove the other ones? So, or how do we find P, in other words, PCA subspace dimensionality? We can do it by Bayesian model selection, by a scree plot, by comparing the ratio with the threshold, where lambda I denotes the eigenvalue related to the jth principal component. Okay, so let's talk about at least two of them. A scree plot. What does it mean? It's a plot of eigenvalues. So sort the eigenvalues in descending order and just plot them by bar plots or whatever. Okay, and see how, of course, it's decreasing, right? At some point, you will see that it decreases a lot. For example, it's larger, suddenly it becomes very small. So that's the cutoff point, right? This is called a scree plot. A good threshold is where the eigenvalue drops significantly, right? Another way is to calculate this ratio. So calculate this ratio, every eigenvalue divided by summation of eigenvalues, right? This shows how much is the percentage of importance of eigenvalue compared to the other eigenvalues, right? So now You can see which percentage is very small, so you remove them. Agree? So now we also talked about how to find P. PCA subspace dimensionality. Now dual PCA. PCA is over. Now dual PCA. The previous one was direct PCA. Now dual PCA. Consider again singular value decomposition of X breve, which is U sigma V transpose, right? Here, give me a second. Oh, okay. U are the left singular vectors, V are the right singular vectors, and sigma is P by P, is a square matrix having P largest non-zero singular values. In this case, I'm assuming in D is much greater than N. What do I mean? Assume dimensionality of data is much greater than the sample size, the number of data points, okay? An example is what? Can you give an example of where dimensionality of data is large? Images, right? Image data. In image data set, the dimensionality of data is the number of pixels. Consider big images, okay? So when D is much large, then we want to calculate these. Okay, well, give me a second. As sigma is a square diagonal matrix and its diagonal includes non-zero entries, right? It is invertible. Therefore, sigma inverse. What is the sigma inverse, by the way? Sigma is a diagonal matrix. As a result, according to linear algebra, its inverse is a reciprocal of the elements of diagonal, right? Okay. So consider these against singular value decomposition. What was linear projection of PCA? It was U transpose. Yes. Do you remember the left singular vectors? U are the solution of PCA. Left singular vectors of X breve. Yes, which are equivalent to eigenvectors of the covariance matrix before projection, right? So as a result, U transpose X breve is a projection, PCA projection. Now replace X breve with its singular value decomposition. Interestingly, U transpose U appears. U transpose U is identity because according to the properties of singular value decompositions, the singular vectors are orthonormal, right? So U is an orthogonal matrix. U transpose U is I, so we'll have sigma V transpose. As a result, another way to talk about linear projection of PCA is its formula is sigma V transpose. Rather than saying U transpose X breve, we can say it is sigma V transpose, where sigma and V are found by singular value decomposition of X breve. Okay. You might say, why do we do that? We will see it in a few minutes. Okay. Why is it useful? Now reconstruction. So previous slide was projection. Now reconstruction. Reconstruction was, do you remember? It was U X breve plus mu, right? In other words, it was U X tilde plus mu. X tilde was a projection, right? So first off, X breve is singular value decomposition. Right multiply the sides by V. So you have X breve V, you will have to use sigma V transpose V. V transpose V appeared according to the properties of SVD. V is an orthogonal matrix, V transpose V is I. So you'll have use sigma. Right? Now sigma here is the pain in the neck. Right multiply the sides by sigma inverse. So U becomes this. Agreed? Now, again, do you remember reconstruction? Was use X tilde. X tilde was a projected data. Plus mu X. We added back the mean, right? What was X tilde? We just found it in the previous slide. It's sigma V transpose. Right? Am I right? Give me a second. No. I apologize. Yes, I apologize. I don't replace X tilde. I replace U. I just found U here, right? So U is X breve V sigma inverse. Also, I have X tilde here plus mu X, right? So far clear? Now, what was X tilde? Now I replace it. X tilde was sigma V transpose. So I replace X tilde by sigma V transpose. Interestingly, sigma inverse sigma appears. Sigma inverse sigma is identity. So it becomes simple. It's simplified to X hat becomes X breve V transpose mu plus mu X, right? So this is reconstruction in dual PCA. By the way, the previous one was projection in dual PCA. This is reconstruction in dual PCA for training data, right? Now, auto sample projection for test data. Again, what happens? So we know that xt tilde was U transpose xt breve, right? Where xt breve is the centered test data, centered by the mean of training, right? So far clear. Do you remember we had this U? We had found it in the previous slide, equations 36, right? Now what do? Let's transpose the sides. So U transpose, we know that transpose reverses the order of matrix multiplication. It becomes sigma inverse transpose V transpose X breve transpose. Sigma inverse sigma is a diagonal matrix, right? Because it's singular values. Sigma inverse also a diagonal matrix. According to linear algebra, its diagonal elements are reciprocal. So sigma inverse is symmetric because it's diagonal. As a result, sigma inverse transpose is sigma inverse. Okay. Now, I replace this U transpose that I just found in this formula. So it gives me this. Xt tilde becomes sigma inverse V transpose X breve transpose X breve T. Agreed? Agreed. In matrix form, if I have several test data points, it becomes equation 40, right? Rather than xt breve, it becomes xt breve matrix, right? Now, auto sample reconstruction. So previously it was. So consider xt hat. It is U xt tilde plus mu X, right? Agreed? So recall equations 36 and 38. This was 36U, right? Which was xv sigma inverse. 38 was U transpose, right? As a result, U transpose, which is used for reconstruction, I replace U with this, and this is U transpose, which we found, right? Here, sigma inverse appears. Sigma inverse times sigma inverse is sigma to the power minus 2. In other words, sigma inverse to the power of 2. Okay? So this is also have, so I have U transpose X breve plus mu X. So I have this. This is, and in matrix form, it is this. This vector becomes a matrix. Vector becomes a matrix, right? So this is reconstruction of test data or auto sample data in dual PCA. Okay. Now let's put all of these next to each other. This is projection in dual PCA, reconstruction in dual PCA, test projection in dual PCA, test reconstruction in dual PCA. Okay. Now recall the fact that D was much greater than N in this case. Okay. Dimensionality of data is large. What was U? What was V? According to what we proved in the preliminaries for the relation of SVD and EVD, V, which is the right singular vectors, are the eigenvectors of X transpose X, right? X breve transpose X breve, right? And U was the, which is the left singular vectors of X breve, are equivalent to eigenvectors of X breve transpose. Okay, what is the dimensionality of X breve? It is D by N. So X breve transpose X breve will be N by N. Clear? Also, X breve transpose is D by D. When D is much greater than N, which matrix is large, which matrix is small? Is X breve transpose X breve large, or is X breve transpose?
D by D will be larger.
D by D will be larger because D is much greater than N, right? U was the eigenvectors of the larger matrix here in this case. V are the eigenvectors of the smaller matrix. U was used in direct PCA. Do you see any U in these equations? They are purely based on V. V is only used in dual PCA. U is used in direct PCA. Calculation of U in case D is much greater than N is hard because you should calculate. Have you done any eigenvalue problem in Python for a large matrix? Either if it is large, either it hangs, it freezes, or it might take 10 minutes. Okay, 5 or 10 minutes. Okay, so direct PCA is not good when D is large. Dual PCA would be useful. Okay, now you see why dual PCA is useful. Now consider a face data set, facial image data set. Apply direct PCA. I have done it. Even a small facial images, not too big, small facial images. Apply direct PCA. It takes 5 minutes. Apply dual PCA, it takes 3 seconds. Okay. This is the difference. Okay. And there is another reason why dual PCA can be useful. Look at these formulas. Do you see these? Also, do you see these? What are these? They are inner products. X transpose X, right? Agreed? What does it ring in your mind? When you have inner product X transpose X? What does it ring in your mind? By the way, here we don't have any X. Here, unfortunately, we have one single X. Ignoring this part, we have either X transpose X or we don't have any X. So it's good for kernel trick. Do you remember kernel trick? We used it in SC and kernel list. So replace X transpose X by phi X transpose phi X, which is kernel. So dual PCA is useful for having kernel PCA. Okay, so far. Now let's start kernel PCA. Any questions so far? No, I need to drink some water. Sorry. So kernel PCA. Consider this figure A. Consider a nonlinear manifold, guys. Consider a manifold or a surface, nonlinear. Okay, you have several data points on it. Do you see that? Green, orange, red, blue. Okay. If you apply PCA on it, what happens? You know PCA finds the most variant direction. What is the most variant direction of these? What is the most variant direction? Is this, right? Agree? Assume, so it is in 3D. Assume I consider P to be 2. I want to reduce dimensionality from 3 to 2. Okay, so this is one. Another principal direction is this. The third one is not that much important, right? So what happens to PCA? PCA projects them, right? Projects them onto this. It becomes figure C. Do you see what happened? The green dot, the green point, collapsed into next to the red point, although they are very far away on the surface, right? Why did PCA fail here, work poorly? Because PCA is a linear algorithm, and our data is on a non-linear surface. You see that? I think this also rings, but in your mind, general relativity. They talk about it in physics too. Assume this is Earth, green is the Earth, red is some other galaxy. If you want to go from the, have you heard of wormholes and these things? How do we go from the green one to the red one very fast? If in the regular travel, we have to go on the surface, but can we find a wormhole? Doesn't matter. It reminded me of that. Okay, so, and that's why general relativity talks about differential geometry. It's about nonlinear surfaces, right? So, okay, so here, PCA fails clearly, right? But the correct way to reduce this dimensionality to 2 is to unfold this surface. And for this unfolding, as you see, it's a nonlinear operation, right? So let's make it nonlinear. So linear algorithm failed. Kernel PCA wants to do kind of, it's a nonlinear thing, right? By the way, I have said it once more previously. When I have nonlinear data, I either should design a nonlinear algorithm, or I transform my data, hopefully it becomes linear, and then I use a linear algorithm. Kernel PCA is the second case. So hopefully I transform my data, hopefully it becomes linear, and then I apply PCA. But this is not in a stage-wise. They mix these two together. So transformation and applying PCA together, right? So kernel, this is kernel between, we already talked about it, right? Phi is the pooling function. We talked about it in kernel SVM, right? And phi transpose phi is kernel. We can have the matrix kernel matrix as well. And now, an important thing, guys. Here, phi of x I have that pulled data to the Hilbert space, reproducing kernel Hilbert space. But what should we do? We should center data in the Hilbert space, because in PCA we have to center data, right? So how do we center data? Phi times h. Agreed? When we said xh, it meant removes the means of the columns of x, so the means of the data. We did use xh in PCA a few slides ago. Now in kernel PCA, we need to have phi xh, right? H is the centering matrix. I denote it by phi breve x, right? So what happens for the kernel when I have centered phi? Phi breve transpose phi breve. Replace phi breve by equation 45. Phi h transpose phi h. Apply transpose in the parentheses. Reverses the order of matrix multiplication. H transpose is h, because h is symmetric. Recall preliminaries. Phi transpose phi h. Interestingly, phi transpose phi appeared in the middle. What is phi transpose phi? It's kernel, according to this. So I have HKH. What was HKH? HKH, recall preliminaries. It's double center kernel matrix, right? So it HKH removes the mean of the mean of rows of K, removes the mean of columns of K, adds back the total mean, right? As a result, for PCA, double-centered kernel is equivalent to centering the pooled data in the Hilbert space. Right. Interesting. Centering pooled data in the reproducing kernel Hilbert space, it means that you double-center your kernel matrix. So we denote the double-center kernel matrix by K breve. Now, recall dual PCA. Do you remember I said we use dual PCA for kernel PCA? Recall it. So recall dual PCA. What did we do in dual PCA? We had X, SVD of X. It was U sigma V transpose, right? Now what happens here? I don't have X, I have phi breve X. Apply SVD on phi breve X, where assume T is the dimensionality of Hilbert space. Okay, it can be infinite, right? And of course, U will be the left singular vectors of phi breve X, and V will be the right singular vectors of phi breve X. And sigma are the singular values, right? But can I find this? Can I calculate equation 47? Can I apply SVD on phi breve X? I can't. Why? Do I have phi breve X? Do you remember I told you in kernel SVM? Usually we don't have phi itself. We have phi transpose phi. We have the kernel, right? Phi itself for some kernels might be known, but for many kernels is not known. So it's not doable to do equation 47 because phi is not known. Phi breve is not known. But let's, rather than applying SVD on phi, let's apply EVD, eigenvalue decomposition on kernel. Because of the same relation that we proved between SVD and EVD. What is V here? V is the right singular vectors of phi equivalent to eigenvalues of phi transpose phi, right? We proved, recall preliminaries, we proved that. What is phi transpose phi? Kernel. That's the reason. It's equivalent to this. So it's the eigenvalue decomposition of K breve, right? V here, I denoted by V, is the eigenvectors of K breve. What is K breve? It's phi breve transpose phi breve. According to equation 47, V, so these two V's are the same V's. V is the right singular vectors of phi breve, or eigenvectors of phi breve transpose phi breve. Do you see that? Okay. So I already explained. As a result, we can calculate the eigenvectors of the double-centered kernel matrix for finding V. By the way, this lambda eigenvalues and this sigma also are related to each other according to the what we proved in preliminaries, right? One of them is the square of the other one. I don't remember which one. Okay. So this is what we had. Eigenvalue decomposition of a double-centered kernel. Oh, yes. This is exactly what I was saying. Lambda is equivalent to sigma squared. Okay. Yes. Now, let's do what we did, like what we did in dual PCA, but for kernel PCA now. So phi breve X is U sigma V transpose. What is projection, PCA projection? In this case, kernel PCA projection. It's U transpose phi breve X, right? So replace phi breve X with its singular value decomposition. It gives you this, right? Interestingly, U transpose U is I, because U is the left singular vector. orthogonal matrix, right? So it gives you sigma V transpose. As a result, linear projection in kernel PCA is sigma V transpose. But how do I find sigma and V? I don't find them by singular value decomposition of phi. Although I use singular value decomposition for proof, but I calculate sigma and V by the eigenvalue decomposition of double-centered kernel matrix. Okay. As you see, its linear projection is very similar to the linear projection in dual PCA. It's different. Why? Because sigma and V are the eigenvectors and eigenvalues of kernel, double-centered kernel matrix. But in dual PCA, they were eigenvalues and eigenvectors of they were singular values and singular vectors of data, centered data X, right? Now reconstruction of training data in kernel PCA. Again, consider SVD of phi breve X, right? So right multiply the size by V. You will have phi breve V. You will have U sigma V transpose V. Interestingly, V transpose V appears, which is identity, because V is a singular vector matrix. And then you will have U sigma. So this sigma is a pain in the neck, right? Multiply the size by sigma inverse. You will have this. This is U. We know that reconstruction is U phi of X tilde, which is projected, plus mu X, add back the mean. Phi X tilde. No. U according to equation 51 is this. This is phi X tilde as before, plus mu X as before. Now I replace phi X tilde with what we found for linear projection in previous slide, equation 50. So if I do that, I will have this sigma V transpose. Interestingly, sigma inverse sigma appears, which is identity. It simplifies to this. Right? Can I calculate this? Guys, can I calculate equation 52? No. Because of this phi breve X, which is a pain in the neck, I don't have it necessarily. Do I have phi breve X necessarily? No. For linear kernel, I have it. But for many of the kernels, I don't have phi breve. I have phi breve X transpose phi breve X, which is double-centered kernel, right? So as a result, in kernel PCA, we can't reconstruct training data. Okay. If we go to scikit-learn, there is no reconstruction for kernel PCA. We can't. Okay. Now, projection for test data, out of sample projection. What happens? U transpose. So what was U? Equation 51. This is U, equation 51. Now transpose it. Transpose reverses the order of matrix multiplication. So you will have this. And I know that sigma inverse is a diagonal, so symmetric. So sigma inverse transpose becomes sigma inverse, right? Then we know that this is projection, PCA projection for out of sample data, right? So I replace U transpose with what I just found. I will get this. Interestingly, this appears. Note that phi breve X, which is this, is the centered pooled training data to the Hilbert space. Phi breve XT is a centered pooled test data. So basically, this is the kernel between whole training data pool and test data. Right? Interesting. So I denoted by K brevity. K brevity is this. The formula for K brevity is KT. So KT is obvious how to calculate it, right? What do I mean? So I have n training data points, one test data point. Of course, KT will be an n-dimensional vector, right? Where you calculate the kernel function. Kernel function can be RBF kernel, whatever kernel, linear kernel, what, right? You know what I'm saying, right? Calculate the kernel function between every turning point and the test point. So KT is known. What is this? 1, n. So it's a matrix of ones. What is this? 1n is a vector of 1. Okay? And n is a number of turning points. But why is KT breve this? KT breve was this. Why is it equivalent to equation 54 C, appendix C in my tutorial paper? It has some proof. I don't want to overwhelm you. Okay? You can go and see the proof. Tutorial, unsupervised and supervised principal component analysis tutorial. Okay. So also, if we have several test data points, xt, capital xt, right? Then in this case, xt breve becomes a kernel, kt breve becomes a matrix, right? Becomes a matrix. Then it becomes this. So this was the vector form, this is the matrix form. Again, C, appendix C in our tutorial for the proof. Okay. So we talked about out of sample projection in kernel PCA. So we can calculate sigma, we can calculate V by eigenvalue decomposition of kernel, centered, double-centered kernel. We also can calculate KT breve according to these formulas, right? So we can calculate everything. Now, out of sample reconstruction. Okay. So what happens? We know that U transpose X is the reconstruction, right? So U, we had it before. U transpose, we also had it before in the previous slide. Sigma inverse becomes sigma to the -2 to the power of -2. Interestingly, this appears, which is the kernel, KT breve. This is mu X. I have it. I have mu X. But this part is a pain in the neck. I don't have necessarily phi X breve, right? As a single term, right? And also for matrix is this. This becomes a matrix. Because of this, again, for out of sample data also, I don't have reconstruction. So in general, kernel PCA doesn't have any reconstruction, either for training or test data. So it has only projection. Why is kernel PCA useful? First off, the choice of best kernel might be very hard. Again, the existential philosophy problem. When you give freedom to the user, you give responsibility to the user, and the user doesn't like it, right? Choice of kernel is a problem of kernel. The kernel PCA is also not always effective in practice. Sometimes it doesn't work well in practice, okay? So why is it useful? It's because there are some papers, again, I have explained it in my tutorial papers. Feel free to read them. Also in my book, Elements of Dimensional Reduction and Mindfulness. Many of the spectral dimensional reduction algorithms are special cases of kernel PCA. Who proved that? Yoshua Bengio et al. The team of Yoshua Bengio. A long time ago, I think it was 10 years ago. They proved that many of these algorithms that you are developing in a spectral dimensional reduction are special cases of kernel PCA. So, for example, PCA itself, MDS, multidimensional scaling, isomap, locally linear embedding, Laplacian eigenmap, they are all special cases of kernel PCA with their own kernels. Okay? Some of them, the kernels are easy, like a formula, simple formula. Some of them you need to have you need to have a piece of code to calculate the kernel, right? Anyways, with some kernels, there can be seen as special cases of kernel PCA with different kernels. You can see reference 18 and chapter 2 in reference 19, also in our book. Supervised PCA using HSIC. First off, let me tell you that we have another supervised PCA using some scoring. For more information, feel free to my tutorial paper. Okay. Before proposal of supervised PCA by HSIC, whenever people said supervised PCA, they were referring to that supervised PCA using a scoring. That's not very interesting theoretically. What they did, they applied PCA, and using some scoring, they used to find some, as far as I remember, sort them and find some things. So I'm saying that it was some kind of sorting, and it wasn't that much theoretically interesting. I don't know why they called it supervised PCA, probably because they were using labels for those scoring. Okay, it wasn't theoretically interesting until Ali Qudsi et al. Proposed supervised PCA using HSIC. But how did they do that? Before that, do you remember Sholkov? I talked to you about Sholkov, Bernard Sholkov. He's the god of kernels. His team is purely focused on kernels in machine learning, and they are in Max Planck Institute in Germany. Okay. So what did they do? They proposed something named HSIC, Hilbert-Schmidt independence criterion. HSIC revolutionized machine learning in various ways. One example is supervised PCA proposed by Ali Qudsi et al., who used HSIC in PCA. Okay, so HSIC was proposed by Sholkov et al. What is that? Consider two random values. Okay, assume you and me. Okay, I come toward you, you go away. I come back, you come toward me. So we have some relation, and we tried a lot, and we see that there is this relation. And this relation is linear, right? And this relation is positive. I go there, you go there too. So this is linear positive dependence. We are dependent on each other linearly. Linear dependence is called correlation. So we have correlation, positive correlation. If I come toward you, you come toward me, opposite direction. Or if I go away, you go away, also opposite direction. This is negative correlation, right? So calculation of correlation is easy. We test whether we are dependent on each other or not. It's very easy. What if I come here, you go in that direction? I come a bit further, you go that direction. It's not obvious whether you are related to me or it's completely random, right? Don't know whether it's random or we're related. So that's dependence in general. And this is clearly, if there is any dependence, this is nonlinear dependence, right? So dependence, calculation of dependence is very hard in contrast to correlation, which is linear dependence, right? So they said that let's pull data from the input space to the reproducing kernel Hilbert space. In the Hilbert space, we calculate correlation, linear dependence. Apparently, calculation of linear dependence in the Hilbert space is a good estimation of dependence in the input space. Very interesting, right? Something which was very hard to calculate in the input space became very easy to calculate in the Hilbert space, right? So that's called Hilbert-Schmidt independence criterion. And I think you know why they called Hilbert-Schmidt. These are the two people who proposed the Hilbert space, etc., and they revolutionized or founded, I think, co-founded functional analysis in mathematics. Because you know that Hilbert space, reproducing kernel Hilbert space, all of these are related to functional analysis, one of the hardest parts of mathematics. Very hard. Also, it's used in quantum mechanics. Okay. So Hilbert was a genius. suppose we want to make, as I said, this is HSIC. HSIC short for Hilbert-Schmidt independence criterion, proposed in reference 21 by Sholkov et al. This is an empirical estimation of that. By the way, if you read paper 21, you will not understand anything. It's very hard. I couldn't understand. Okay, I just could understand this formula. Okay. So Sholkov's papers are usually very hard. So what is this? What is it saying? What is this? Can you tell me? HKH. So by the way, this HSIC is between two random variables, K and X and Y, for example. Okay. So KY is the kernel on the Y data. Kernel matrix of Y data. KX double dot, you don't care about my double dot. There is a reason. I wouldn't want this to be confused with something else. KX double dot or KX is a kernel over X data. What is HKYH? It's double centered KY. Kernel over Y data. So basically it says that, by the way, what is trace of this and trace of, for example, because this is a matrix, right? Trace of matrix A, B, or A transpose B, doesn't matter. It's the inner product for matrices, recall preliminaries, right? So basically it says that double center one of the kernels, also consider the other kernel, calculate their inner product, and you feel free to use some scale, 1 over n minus 1 to the power of 2, right? N is the number of points. This is HSIC. And it shows the dependence between X and Y. It's very interesting. Okay. H is the center in matrix. If X and Y are independent, HSIC is 0. If they are dependent, HSIC is greater than 0. So it's a non-negative measurement, but there is no upper bound. This is a flaw of HSIC. There is no upper bound, but there is a lower bound, 0. 0 means they are independent. Okay. The greater the HSIC, the greater dependence they have. Okay. Now, how did they? I think we don't have time. We don't have time. We'll continue with the next session. Okay. Thank you. Thank you.